What's up, Cal gang? Welcome back to some physics. So let's solve this problem. So we got some pulleys going on, right? So we have these two blocks attached to each other by a pulley. The red one is hanging and the blue one is being pulled across the friction surface here. So initially the system moves at 0.9 meters a second, right? So the block is moving right 0.9 meters a second, and this one's moving down 0.9 meters a second. Then we know that the blocks are going to come to rest after moving 2 meters. So this one's going to move down 2 meters and this one's going to right 2 meters. Now we want to find the coefficient of kinetic friction between the table and this block here. So it's kind of like not giving a lot of information and it looks really complicated, but we can use the work energy formula to figure it out. So first of all, what's the equation? Well, work non-conservative is equal to the change in energy. So this is telling us that any of the work, right, done by things that are taking energy out of the system is going to result in that change in energy. So our non-conservative work, right, that's going to be the friction of the table. That's what's slowing the blocks down. So work non-conservative, we can go ahead and plug in the work done by friction, right, is equal to the change in energy. And so what energies do we have in the system? Well, let's think about all the energies that we've learned so far. So we know the gravitational potential energy. Let's think, is that going to count? Well, we have this block, and it's going to move down a distance of 2 meters. So there's going to be some change in gravitational potential energy. So let's add that to the system. Now we have kinetic energy, because we're moving initially with a velocity, and then we're going to come to rest. So our kinetic energy is changing. So we need to account for the change in kinetic energy. Then what else is there? I think it's just that, right? Yeah, so the blocks are moving up and down and the velocities are changing. So there's no springs in the system, so we don't have to worry about that spring potential energy or anything like that. Let's get rid of that. So let's look at these changes of energy, right? The work of friction still stays here. So let's see, delta, right? Delta is final minus initial. So let's write gravitational potential final minus gravitational potential initial. And then this kinetic energy can become kinetic energy final minus kinetic energy initial. So let's figure out what is changing. So let's see, final gravitational potential energy. So this block is going to start here, and it's going to move down a distance of 2 meters, right? So we can take that basically the base of the system is 2 meters down. So we're going to say that our final gravitational potential energy is 0, because we're going to go down a distance, and then our initial kinetic energy, or initial gravitational potential energy, is going to be 2 meters up from that point. So that's kind of why we're choosing to do this. You could also go through and you can make delta U is equal to mass, gravity, delta Y, where delta Y is 2 meters. It's going to give you the same equation, but you just got to make sure to keep that, and that should be a negative too, so you're going to think about doing it that way. But this way works just fine too, so let's do it this way. So kinetic energy final. We know that the blocks are going to come to rest, so we're taking our final condition to be after the blocks come to rest. So final, we're going to set that equal to 0, because they're going to have no velocity at the end. However, we know that they have an initial kinetic energy, so that's going to be equal to something. So now let's go ahead and expand this equation, now that we know these are equal to 0. So what is the work of friction? Well, work is force times distance. So what we can do is we can label this force of friction times distance. And we know what this distance is, right? We know that we travel 2 meters, so this distance is going to become 2 meters. And we're going to set this equal to this side, so it's going to be negative U gravity initial minus kinetic energy initial. Okay, so let's move on. So we know that force of friction is equal to coefficient of kinetic friction times normal force. So this can be replaced with that. And finally, we have our variable, coefficient of kinetic friction. So let's set that equal to what we have here. So gravitational potential energy is going to be negative mass, gravity, height. And kinetic energy is going to be mass, or 1/2 mass velocity squared. So before we get complicated here, let's make sure we know what each of these variables are assigned to. So friction, where is the friction in the system? The friction is only occurring for this 8 kilogram box. This box has no friction attached to it. So when we use the force of friction, we only have to account for this 8 kilogram box. And so let's specify that this normal is for the 8 kg box. Then for this mass, the gravitational potential energy, which box is gaining gravitational potential energy? it's going to be this box, right? This is the only box that's changing height. This box is not changing height. So we have to account only for the 6 kilogram mass here. Right, so this is 6 kg mass there. And then this mass is the kinetic energy of the whole system. Now, because both blocks have an initial kinetic energy, that's going to be the mass of 8 kilograms plus 6 kilograms, right? So this is going to be 8 plus 6 kgs. All right, so let's rearrange this equation for what we're looking for. So we're solving for the coefficient of kinetic friction. So let's go ahead and divide by normal and distance. And also, really quickly, we can replace this normal right now with mass. It's equal to the mass of that 8 kilogram times gravity, right? Because if we were to draw a force body diagram for this 8 kilogram box, and why don't we do that? We have the mass of it pointing down. This is force gravity. It's equal to mass times acceleration, or mass times gravity, I mean. And then, of course, the normal force is pointing back up. And this is the normal force. So we can see, because this block is in equilibrium, right? Some of the force is y. I guess we can go write that over here. Little side, some of the force is y for that block, 8 kilograms. Has to be equal to 0 because we're not accelerating in the y direction. And it's equal to normal minus force of gravity. So if we move that over, you get that normal is equal to mass times gravity. So that's what we're going to plug in for normal. So then, we rearrange this equation. Coefficient of kinetic friction is equal to negative, so the mass of this one is 6 kilograms, so let's plug in 6 times gravity times height minus 1/2. This one is 8 plus 6 kilograms, so let's plug in 14, and then velocity squared. And then we're dividing by, again, the mass of the 8 kilograms, so we're going to divide by 8 times distance, and this is our equation. So let's plug in everything else. Coefficient of kinetic friction, right, so we have negative 6, gravity is 9.81. Height, right, this goes 2 meters down, so we're going to add that 2 meters. And this is going to be minus 1/2. 14, velocity initial is 0.9 squared. And then 8 times the distance of 2 meters. And then really quickly, I totally forgot to do this, but work non-conservative, the work of friction is taking energy out. So there's supposed to be a negative sign all down here. So this is going to be negative, and then a negative could get distributed. That's going to make these positive, just like that. So you solve for this, you get that the coefficient of kinetic friction is equal to 0.786, and it's unitless. So there you go, that's how you use that work energy formula for this problem here. So yeah, any questions, feel free to ask in the comments below. Check out my playlist for more problems like this, and I'll see you in the next video. Peace.